All right, in this video we're going to look at graphing sine and cosine onto a Cartesian plane. And to do that, we're going to look at a table of values first of all. Hopefully by now you've sort of got an idea as to the symmetry and repeatability of the unit circle. And the graphs of the sine and cosine run off that, and these are called periodic functions, and hopefully you'll see why they're called that. So first of all, with this table of values, I've put in start angle and end angle. So this is one full revolution around the unit circle from 0 to 2 pi. All right, now a couple of things. The sine function we'll look at first. It looks like this. Y equals the sine of the input. All right, now the input in this case is the angle. Even though I've referred to it as x, don't get confused and relate it back to the unit circle and the location of the point on the unit circle. Even though the location of the point on the unit circle, the x value is cosine, that's got nothing to do with the sine function. All right. What we're looking at here for the sine function is we're splitting up the sine and the cosine and looking at the patterns that occur as the point moves around the circle. All right. So a little bit confusing, but you'll get the hang of it. Okay, so the input is the angle, the output is the y value. Okay, and that's what we're going to be graphing along the x-axis. Okay, so the graph, most of the time, depending on the revolutions you're asked to graph, the graph will look like this. And you notice that it's different from a Cartesian plane in that we don't tend to show the x-axis to the left. I'll explain why. All right, so let's go through. First of all, 0. So this is the angle. We're asked after the sine of the angle when it's 0. So remember the sine of the point when the angle is 0 is the y value, and the y value when the angle is 0 is also 0. It's at 0 height. All right. So the next angle we looked at was pi on 6. This was equivalent to 30 degrees. And we know, you hopefully remember that the sine of pi on 6 was a half. The next angle was pi on 4, and hopefully you recall that the sine of that was root 2 on 2. The next angle in the first quadrant was pi on 3, and the sine of that angle was root 3 on 2. And then the last angle, the last angle in the first quadrant, or of the first quadrant that we look at, is pi on 2, and the sine of that angle was 1. So you can see there's a bit of a pattern. It starts from 0 and gradually works its way up to 1. And if you're not quite sure what those are as decimals, you got 0.5 there. Root 2 divided by 2 is, root 2 is 1.7, I think. Square root 2, no, 1.4. That's what it is, 1.4. So the divided by 2 is roughly 0.7, and then root 3 divided by 2 is going to be in between 0.7 and 1, so it's going to be a bit of an ascension there. All right, so you can see that there's this gradual increase across 0 to 1. All right, now in the next quadrant, the next angle we looked at, or we can look at, is going to be 2 pi on 3. The next angle is 3 pi on 4. And then the other angle after that is 5 pi on 6. Now, if you remember back to your symmetry, all you're looking for is to relate it back to a reference angle in the first quadrant. All right, so given that this one is a over 3, denominator of 3, it's a reference angle of pi on 3, which means that the sine is going to be the same as this one. We just have to work out whether it's positive or negative in that quadrant. And given that quadrant 2 has a positive sign, it's going to be root 3 on 2, the same. The next one, the denominator is 4, so the reference angle is the same as pi on 4 in the first quadrant. Given that sine is positive in the second quadrant, it's going to be the same as that one. 5 pi on 6, you're starting to see a pattern, I hope, is the same as pi on 6 in the first quadrant, so it's going to be a half. Now what we've seen here is a gradual increase from 0 up to 1. All right. And now we're starting to see the reverse because the numbers are mirrored across this boundary of 1. So root 3 on 2, the same. Root 2 on 2, the same. And then 1/2, the same. And in the last one, the sine of pi, which we know is 180 degrees, is going to be back at 0. So we've seen this increase up to 1, and now we're seeing a decrease back to 0 in the second quadrant. All right, now the next angle in the third quadrant is going to be 7 pi on 6. The next one is going to be 5 pi on 4, and the last one is going to be 4 pi on 3. And I won't give you any prizes as to what those values are going to be. 7 pi on 6 being a multiple of a pi on 6 angle means that it's the same value, a half. We just need to know whether sine is positive or negative in the third quadrant. Given that it's below the x-axis, it's a negative. All right, so we're starting to see a dip now. We've gone from 0 up to 1, back down to 0, and now a negative has started to appear. So theory might be the next one will also be negative. 5 pi on 4, given it's a multiple of 4 in the first quadrant, it's going to be the same value. Sine is always negative in the third quadrant, so it's a negative. And then the last one is going to be minus root 3 on 2. So you're starting to see this pattern. It's going up to 1, down to 0, down to minus 1. All right, and the angle in the bottom quadrant there is 3 pi on 2. All right, and then the last three, coming back around into the fourth quadrant, the angle is 5 pi on 3, and then 7 pi on 4, and then 11 pi on 6. We'll fill in the 2 pi angle first. That's back at the x-axis. We know that the sine of the x-axis is either 0 or 0, so that's also 0. 5 pi on 3, given that it's a multiple of a pi on 3 angle, it's going to be the same as in the first quadrant, root 3 on 2, sorry. Root 3 on 2, given that it's in the fourth quadrant and below the x-axis, it is also a negative. All right, and we're starting to see this symmetry occurring again, where this one is the same as the 2 before. So hopefully that means that these two are the same. Let's have a look. 7 pi on 4, a multiple of a pi on 4 angle, so it's the same again. Root 2 on 2, and then minus a half for a pi on 6 angle. So as you can see, it's gone a half, getting bigger out to 1, and then smaller, smaller, smaller to 0, and then smaller, smaller, smaller to negative 1, then bigger, 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 back up to 0. All right, so we've seen this cyclical function occurring. Now, as we come to put this onto the x-axis, we're actually going to mark the angles along the x-axis. So this first angle here is going to be 0. The last one is going to be 2 pi. Now, I don't expect you to accurately mark out pi on 6 and pi on 4 and pi on 3. There are easy ways to do this, and I'll explain to you how. You notice here that I've got my end markers. I've also got a middle, and I've also got quarters. So let's just mark halfway and call that pi. We'll mark quarters and call this 3 pi on 2, and the other quarter and call this pi on 2. Then in between each quarter I've got 3 angles, so I just have to split it up into 4 parts like so. So you chop it in half, put a tick in between each one, and there is your unit circle. All right, now I don't expect you to mark each of these intervening thirds. You can if you wish to. All right, I don't expect you to do it because my one's quite small and it might get a little bit messy as we do it. So then the next step is just to graph them, graph each coordinate point. So 0, 0, there's 1. Pi on 6, last thing I had to do was mark the top of this as 1 and the bottom of that as -1. All right, those are the biggest and smallest y values that we have. So we don't need to go any further than that. All right. Now mark the coordinate points. We have 0, 0. We have pi on 6 is up at a half, which is roughly here. Pi on 4 is up at root 2 on 2, and you're not going to get this right. It's not going to be exact. It's a third, so don't worry about that. Just put it roughly in. The next one is here, and the last one you can see is going to be right at that 1 value. All right, so we've seen this curve. Not a very good one, but it's still a curve. All right, now after that we notice that it was decreasing, and it's going to be symmetrical. So this value here is going to be mirrored across the 1, and the same for the next one, and the same for the next one, and the same for pi, which is out at 0. So we continue the curve down like so, and we notice that it then drops below the x-axis, but it's going to be the similar values. So it's going to minus a half, minus root 3 on 2, oh, so yeah, minus root 2 on 2, sorry, minus root 3 on 2, and then dropping to negative 1 here. All right, and again, you're not going to get this 100% right. They're exact surds, they're exact values. It's not going to look uber perfect. You've just got to get that nice curve. All right, so we join it up like so. And there is one complete revolution of the sine function. So there's a few features that we like to talk about here. You can see that sine functions start at 0 and end at 0. All right, at a quarter of the way through, they're at their maximum, and 3/4 they're at their minimum. Okay. We also like to point out that it's symmetrical around the peaks. It's also symmetrical around halfway. There's lots of symmetry that we can see here. All right. After 2 pi, which I haven't shown, the expectation is, as you can see, that it's gone back to 0, and the next angle is going to be 2 pi plus pi on 6, which will be again a first quadrant angle, and so therefore it'll be a half. So you can see that the extension of this will be the same thing again, repeated. And that's why this is called a cyclical function. So there's one cycle, and then it restarts and becomes a second cycle, and so on. All right, so a few terms to get through with this. Where it starts to repeat itself, so from this point onwards I'm going to erase, all right, and now that point where it's reached, and between there and there, this is known as the wavelength. All right, now this is where it starts to draw from ideas of waves like water, sound, light, all travel in waves, and this is what a wave looks like. Okay, so that's called wavelength, the distance from the start to where it repeats itself. All right, where it repeats. Okay, this point here is called the max, obviously. This point here is called the min. All right, the middle, that point there, is called the mean position. All right, now obviously that mean is referring to an average position. All right, so if you averaged out the max and the min, you would find that they were at 0. So -1 plus 0, and that's the mean position for this graph. All right. The last thing to think about is the distance from the max to the mean position is called the amplitude. Okay, the amplitude is basically the height of any of the waves, and notice that the amplitude is not the distance from max to min, it is the distance from max to mean position. All right, the amplitude is the height of the wave. Okay, so a few things to write down, and I would copy this into your books right now. All right, I'm not going to derive the graph of cosine the same way I did the first one, so I'll show you the shortcut to doing it. We've drawn up our x-axis with the angles labelled. We've also going to put the max and the min there because they remain the same given that it's from the same unit circle. And I'm not going to put in the 3 angles in the middle here because the shortcut is that we don't need them. All right, now cosine is a bit different. We know that from the unit circle, cosine is the x value of the point here. So cosine, if the point is out here on the x-axis, cosine starts at 1. So cosine starts up here. Now as the point gets around to the top of the first quadrant, it jumps onto the y-axis, which means that the pi on 2 angle result is 0. All right, then moving back around into the second quadrant, it hits the x-axis again, so it's going to be at its lowest point for the angle pi. Then it jumps back up to 0 when it's vertically downwards, and then coming back around to 2 pi, it meets back up at the max again. So cosine actually looks like this. All right, now you don't have to draw straight lines. You do want to make sure it's a curve. All right. So it goes through there, bottoms out, at pi, back up through 3 pi on 2, and hits there. Okay, so this is a cosine. You might remember that the sine graph looked a little bit different. So you can see the sine graph here on the left starts at 0, goes up, and then down, and then up again. Cosine starts at 1, goes down, up, and then levels off. All right, so cosine looks different from sine. There are some special words we use to describe it, but we can go through those later. All right. What you need to remember is that the table that I gave you last lesson with your exact values. All right. This table here will help you graph sine and cosine and tan when we get to it. All right. As I demonstrated with the sine graph, all you need to remember is the exact values and then change the sign in front of them depending on the quadrant that they are in. And it's the same with the cosine. All right. So if I was to put in these angles here, I would say that this was pi on 6, this was pi on 4, and this was pi on 3. And then these are the values, root 3 on 2, root 2 on 2, and a half. And they would be here, here, and there. And you can see that what I've drawn is actually pretty damn accurate, if I don't say myself, even though I was freehanding it. All right, so doing that curve, laying the groundwork with the main angles first is a really good way to start it. You don't have to go through the long step of getting the table of values indicated first. All right.